In this section we're going to be working with regression, and in particular linear regression. So we're only going to be looking at the case when our data appears to show up in a linear pattern when we talk about the x versus y scale. So for instance, if we did a scatter plot of our data, and let's say we just kind of have some random mix of points that end up looking something like this, it appears that they're pretty linear, meaning as x increases, so does y. So you can see that a line of best fit might look something like this, or it could look something like this. There's quite a few different lines that look like could fit pretty well through here. But we're talking about regression, and regression in particular is basically the mathematical line of best fit. So in other words, we use mathematics to calculate the line that fits the best. Now the example that we have here is definitely a linear correlation. They are, as x increases, y increases, they're very tightly clustered along the line with all these data points. We could also look at other graphs, other scatter plots that aren't that. But before we get into there, let's go ahead and talk about our line of best fit. Our line of best fit, instead of being called y equal mx plus b like we're used to in college algebra, we're going to call y hat. We call it a hat because it's an estimate. And we will look at this as ax plus b. Now sometimes on your calculator when you're working, it might show up as a plus bx, so you have to be really careful that you keep a close eye on that. Basically the coefficient in front of x is your slope, so in this particular case a is slope, but depending on which function you choose on your calculator, a could also be the y-intercept. So we have to be really careful. As I have it written here, a is the slope and b is the y-intercept. Now the y-intercept is where it crosses the y-axis. Now y hat, like we said, is our predicted value. So we would plug in some value of x and we'd come up with a predicted value of y. Now the line of best fit is this y hat then. Let's see, it's equal to this one right here. So this is our y hat equals a plus bx, we'll say. Now we have to be careful when we're doing prediction. If these values, let's say, run between 1 and 10, I wouldn't want to do prediction at 50 or 100 because I don't know what's going on out here. I only know what's going on within this cluster of data. So we have to be careful about staying within the range or close to the range of data in order to do prediction. Now we could also look at another scatter plot. So this scatter plot might have looked linear for a little bit, but as we look at the whole plot, we can see, you know what, there's not a straight line going through here that is predictable. So I could say, well, I think it might be here, and somebody else would say, oh, well, I think it could be here, and you're both right. There's another one here. So there's a lot of different lines of best fit here that don't really have any pattern. They're not all positive slope, they're not all negative slope. So this has no linear correlation. There's no pattern to my data here. I could also look at another scatter plot. And this scatter plot will definitely have some sort of a correlation, but it's just not linear. So if we look at this, this looks like a nice parabola. So this definitely has correlation. As x increases, y increases until I get to a certain point, and then it starts to decrease in a predictable manner. So I do have correlation here, but not linear. And what we're focusing on in this particular lesson is all linear correlation. Now, how do we go about this? Well, when we're talking about our steps for linear correlation, what we really need to be aware of first is, are the data correlated in a linear fashion? So our steps for linear correlation: the very first thing that you must do is you must check to see if the data, x and y, are linearly correlated. So again, this is last section when we looked at the correlation coefficient rho. This is where rho equals 0 or rho does not equal 0. The case where rho equals 0, this is where we have no linear correlation. If the data is not linear correlated at all, what we do then is we use y bar for prediction. And we'll talk about what this means here in a little bit. In the second case, where there is linear correlation, we use our line of best fit, the y hat equal a plus bx. Now, a plus, I want to be consistent here. Let's ax plus b, we'll say. Now your calculator switches this back and forth on you, so be really careful. A will not always be your slope, B will not always be your y-intercept. And when we're using our calculator, I'll make sure I point that out to you when we run across that case. So we're going to use our line of best fit, or regression line, for prediction. If we show that the correlation coefficient is not 0. So once I have whichever case this is, then I would use y bar for prediction, and I would be done up here if I fail to reject HO. If I reject HO, then I would use my line of best fit. So if you decide, whoops, I thought that was my eraser. Try it again, there. So if you decide there is no linear correlation, you will use y bar for all predictions. Okay, and we'll see some examples like this. If you decide there is a linear correlation, we're going to use that line of best fit. And I want to make sure I get these in the right order. AX plus B for prediction. So if we decide there is no linear correlation, I'm going to use y bar for any prediction I want to make, and I'm done. Okay? If I think there is some sort of linear correlation, then I'm going to use my linear regression equation. Okay, so that's where my step 2 would come in. So under here, what I would do then is I'd enter the data in L1 and L2. Which you probably already have entered if you tested the correlation coefficient. Then we would calculate the line of best fit. Now there's two different ways to do this line of best fit. One way that we could look at this line of best fit is we could look on our calculators under Stat, Calc. So we go to the Stat button, look under the Calc menu, which I think is arrow over 1, and then look at linear regression, AX plus B. Now if you look further down from this linear regression AX plus B, there's a linear regression A plus BX. It doesn't matter which one you use, you just have to be very careful about which coefficient is your slope and which is your y-intercept. And there's another place that you could go to under Stat, Tests, and then there's a linear regression t-test as well where you could find this information, and I'll show you that as well when we get a little bit closer. Now because we already decided there's a linear correlation, and we did this with a hypothesis test, that means that we can use this for prediction. So use my line y hat equals ax plus b for prediction. Because we've already established that it's appropriate to use linear regression because we've established that there's a linear correlation between the variables. So we're going to look at quite a few different examples. And again, one of the important things we need to remember is we have to establish that there's some sort of a linear correlation before I can use linear regression. So first example, what we want to do is we want to look at some summary data that's provided to us and then run through all the different tests that we have here. Okay, so for this particular example, we're looking at IQ scores. So it says, suppose IQ scores were obtained from randomly selected twins. So each twin set is recorded as basically an X value and a Y value. We have 20 such pairs of twins, and we already know the linear correlation coefficient is 0.845. So there's a lot of information here, so let's go ahead and circle the relevant information. This is R. This is our sample correlation coefficient. And the equation of the regression line they give us too, we don't even need to predict that or plug it into our calculators. They give it to us. Now X represents the IQ score of the second born. And so that means Y would equal twin born first. So let's kind of keep track of some of this. It says also the 20 X values have a mean of 98.14. Okay, so let's go ahead and summarize this down here. We're running out of space. So X is the twin born second. And the average IQ of the second born twins, that's from right here, is 98.14. Okay, and then we have Y values. That's our firstborn twin. So this is Y bar, in this case, is 99. Now these numbers are very, very close. The Y bars are a little higher, so we might be able to say, you know what, it looks like the firstborn twin has a little bit higher IQ. But the difference between 98.14 and 99 is so small, I doubt that it's statistically significantly different. But we're actually not looking at that. We're not going to do a hypothesis test on that. What we're doing is to see whether these are linearly correlated. And so that kind of comes into play with this value of R. R is my sample correlation coefficient. This is the strength of the linear relationship between X and Y. This is the strength of the linear relationship or the linear correlation. Now notice we're using linear. So again, the strength of the linear correlation between the IQ score or the IQs of second-born twin and firstborn twin. And this value is equal to if we scroll up a little bit, pretty high, 0.845. Okay, now let's see what other information they have for us. We already recorded these averages here. It says, what is the best predicted IQ of the twin born first, given that the twin born second has an IQ of 99? So we want to predict our IQ score for the firstborn twin. So we want to predict firstborn IQ given secondborn IQ of 99. So we want to, if we want to put this in terms of X and Y, we want to predict Y hat given X equal 99. Because second-born, again, is our X value. Well, what we don't know is if I can even do this, because in order for me to do this, there has to be a linear correlation between these variables. So to get started, if you remember up above what we had our steps of linear correlation, our first step was to check HO versus HA. Well, this is actually the longest part of the process. So this is a review from our last section. We test rho equals 0 versus rho not equal to 0. This is no linear correlation. And over here, down here, this is some sort of linear correlation. Okay, so my steps here then are to state HO and HA. Second, for this test, is I would let alpha equals 0.05. Now that's given to me up above. We're also given that R is equal to 0.845. And this is my test statistic. Actually, let's organize this a little bit differently. We're going to have all the same values. I just don't want to try and squeeze them all on one screen. And let's renumber these. So again, we're looking at steps for linear regression. So my first step is to check to see if there's a linear correlation or not. So within this first step, this is my first step, if that makes sense, to check to see if I have a linear correlation. My second step is alpha equals 0.05. My third step is to go ahead and calculate my test statistic. Now for this particular case, my test statistic is just my value of R, which is 0.845. Now remember, we can also use the p-value approach to this as well, so if you'd rather do that, you can. I'm going to be using the tables here. Step 4 is we need a critical value. And in order to use my critical value, I need to know alpha is 0.05, and I need to know my sample size was the number of pairs of twins. In this case, we can see that that was 20 such pairs, so sample size is 20. And then let's go ahead and pull up our table. So our table for our Pearson correlation coefficients, and remember these are in my math lab along the side tab if you need to look those up. And let's get a good copy of this one. We're going to come right down here to 20. And then we'll also make up some sort of a rule for when we reject or fail to reject. So we're looking under this column, the 0.05 and the 20, and we're seeing that these cross at 0.444. So my critical value is plus or minus 0.444. And it's actually just, because we're always working the absolute value, so we usually just look at the positive of that. Okay, so now I'm going to have to make a decision. Before I actually make my actual decision in step 5, let's go ahead and look at our decision rules. So we will reject HO if the absolute value of my test statistic R, which is right up here, is greater than 0.444, and we will fail to reject HO if the absolute value of my critical value is less than 0.444. Now these are all the tests that we did back in the previous section, so these should look familiar to you. Okay, so we actually are going to make some sort of a decision now. So in order for me to make our decision, I need to know R, which was 0.845, and I need to know my critical value, which was 0.444. Well, we can see pretty clearly that the absolute value of 0.845 is greater than my critical value of 0.444. Therefore, we will reject HO. Now, when we reject HO, that means we have support for my alternative hypothesis. So my alternative hypothesis, we rejected no linear correlation. So that means we do have some sort of a linear correlation, and that would make sure that shows up in my summary. So my summary, the data supports the conclusion. There is a linear correlation, it has to be linear, between second-born IQ and firstborn IQ. Therefore, and this is kind of the important part of this whole conversation, linear regression prediction is appropriate. So linear regression prediction is appropriate. Okay, so since that's appropriate, that means I can go on to find my linear regression line. Okay, so what we did here, this step 1, was we determined that there is a linear correlation, and because there was a linear correlation, prediction is appropriate using y hat. Now, step 2 of my steps for linear regression are to enter the data into your calculator. So here, enter the data in L1 and L2. In this particular case, this is done for us. Okay. Step 3 would be to calculate the line of best fit. And in this example, this is done for us as well. And they give us the line of best fit to be y hat equals, and again, this was given to us in the original equation, or the original problem I should say, as 12.36 plus 0.88x. 12.36 plus 0.88x. Okay, now remember, x was our second born. And so y would be our firstborn, just as a reminder. Okay, now step 4 would be to predict if appropriate, and we've already determined it's appropriate. So we want to predict y hat when x, in this particular case, was equal to, I think it was 99 or 100. Oh, here it is. Predict the firstborn IQ given the secondborn IQ of 99. Predict y when given x equal 99. That should be a 9 there. So predict y when x equal 99. Okay. So this would mean y hat is equal to 12.36 plus 0.88x. X in this case is 99. So let's go ahead and grab our calculators. And we're not doing anything statistical with this, we're just plugging it in and calculating. We have 12.36 plus 0.88, make sure we get the decimal in there, times 99. So we get 99.48. Now that seems reasonable. If you think about what our data is, they're all right around 100, so that seems like a reasonable prediction. Now if we would have gotten something like 482 for the predicted IQ, then we might want to wonder. Now we always have to be careful here about rounding appropriately, because a lot of times they'll say round to one place or two place, so make sure you're reading those directions. But basically I predict 99.48. Okay. So for a second-born twin IQ score of 99, I would predict a firstborn IQ score of 99.48. So that's basically my summary here. Now I was able to do this because linear correlation was appropriate. If I had found that linear correlation was not appropriate, then I would have just used y bar for my prediction. So we have to be really careful here about making sure we test to see if linear correlation is appropriate before we do anything. Now the next problem we're going to look at, instead of being given the summary data, we're going to be given the raw data, and then asked to work from there. So let's read through this one. First of all, it says the data show the chest size and weight of several bears. Find the regression equation, letting the first variable be the independent x variable, and then find the best predicted weight of a bear with a chest size of 57 inches, using a significance level of 5%. So first of all, in order for us to get started on this, it's good to understand the idea between independent and dependent variables. They're telling us that the independent is this chest size. So this is my x random variable. So x is my chest size, my weight is pounds. So this is going to be L1, this is going to be L2. So what this is saying is the weight of a bear is dependent on his chest size. So as chest size increases, you might think that the weight of the bear would increase. And this would be a really nice thing if they could just measure a bear's chest size. Let's say if they had sedated a bear, they could predict its weight with some accuracy and not have to actually get it onto a scale. So that would be handy. So we're going to test this from beginning to end. And to get started here, we need to go through the tests and check to see if there's a linear correlation here. So I think the first thing that we should do is to enter our data in L1 and L2, calculate the correlation coefficient, and look at a scatter plot. So let's go ahead and open up our calculator. We're going to go to Stat, Edit, L1 and L2, and if you have data in yours like I do in mine, make sure you clear those out. You go up to the heading L1 or L2 and hit Clear and enter the data. So for us, L1 is going to start with 58, 48, 51, 58, 44, and 60. Okay, now L2, I need to make sure that 58 is paired with 425 pounds, 48 is paired with 266, etc. So we have to be careful that we enter these as pairs. Okay, so now that we have these entered as pairs, let's go ahead and let's do a scatter plot. Let's look at a scatter plot of this real quick. So that's second stat plot. Now I want to choose plot 1, and when we choose plot 1, I need to make sure first of all that I turn stat plots on. Scatter plot is my first option I have here. Now my X list was L1, and remember I noted that here. My Y list is L2, and I can go ahead and hit graph. Now I might not see anything, so if I don't see anything, I need to go to zoom and zoom stat. Now for me, zoom stat is option 9, so I'm just going to hit 9. You could also arrow down. So this is my scatter plot. It kind of does look like it could be positively correlated in a linear fashion. Okay, so that looks like it could be reasonable. So let's go ahead and put that into my data output here so it can kind of get an idea if linear correlation seems appropriate. So the scatter plot now, just looking at the scatter plot's not good enough, but it gives me an idea. The scatter plot looks like there could be a linear correlation. So now we actually have to go through and check. So the next thing I want to do before I get started, I want to calculate R. I want to know what my correlation coefficient is. So let's see if I can remember. Let's go to Stat, and I think it's under Test, but let's look through Calc here real quick. I don't see it, so let's go to Tests and then scroll down. And it's going to be right down here under, here it is, linear regression t-test. Now linear regression t-test gives us a lot of other information that we don't really care about right now, but it gives us our correlation coefficient. Now if you don't have this menu, what you would do is you'd go second L1, comma, second L2 to tell where you're trying to find the linear correlation. I don't really care about the not equal to case or the linear regression equation right now. What I want to just do is go to calculate. So this is my screen, and I'm looking for an R. Let's scroll down. Here's R squared. So here's my R value. So that is my correlation coefficient. That's really high. If you remember, my correlation coefficient, the biggest it can be is a 1, and that's for a perfect positive linear correlation, and this looks very high. So this is my value for R. So we'll say R equals 0.9241. This is my sample correlation coefficient. And I should say sample linear correlation coefficient. And it basically tells me the strength of the linear correlation between the two variables. So the strength of the linear correlation between my two variables. And my two variables were chest size and weight. Okay, so now I want to be able to answer the question, find the best predicted weight of a bear. Well, I don't know if the best predicted weight of the bear would be a linear regression line, a y hat, or if it would be y bar. I'm not sure of this yet. So let's go ahead and do our steps of linear regression. So let's go ahead and go through our steps of linear correlation, or linear regression. So step 1, we want to check to see if there is a linear correlation between chest size and weight. Okay, so if I'm trying to see if there's a linear correlation between chest size and weight, my first step would be to state my HO and HA. So HO is my correlation coefficient is equal to 0 or not equal to 0. So this is no linear correlation, and this is linear correlation. Okay, so in this particular case, alpha is equal to 0.05. That's my step 2, and step 3 is my test statistic. And that was R equal, here we are, R equals 0.9241. Okay, let's go ahead and look at our critical value now. In this particular case, my critical value, I need to know two things. I need to know my sample size, and if I look up here, my sample size was 1, 2, 3, 4, 5, 6 pairs. So my sample size is 6, and my alpha value is 0.05. So let's go ahead and look at our table. So our sample size is 6, so I don't need a very big chunk of this table. Now if I have anything more extreme than the critical value, that means I can reject HO. So I'm looking across from 6 and down from 0.05, so that's 0.811. So my critical value is equal to 0.811. So let's go ahead and talk about our decision rules. If the absolute value of R is greater than my critical value, I'll reject HO. And if I reject HO, that means there is a linear correlation. Now, if the absolute value of R is less than my critical value, I'll fail to reject HO, and then there is no linear correlation. Okay? So now I'm going to make my decision. So for me, my correlation coefficient was 0.9241, I believe. Let's go check that. 9241. My critical value is 0.811. Well, it's pretty clear to see that the absolute value is 0.9241 is greater than my critical value of 0.811. So I'm right up here, I'm going to reject HO. And so that means there is a linear correlation. Okay, so let's go ahead and look at my summary now. The data supports the conclusion that the variables chest size and weight are linearly correlated. And because of this, or therefore, linear regression prediction is appropriate. That means I can use the y-hat. Okay, so that means I can go on to step 2. So step 2 was enter the data in L1 and L2, which we already did because we already have our value of R. Step 3, calculate basically our line of prediction, our line of best fit. And this is actually my regression equation. Okay, so let's grab our calculator. Now we already have all this data in here. So this is actually my line of best fit. It's already given to me right here. This is a plus bx instead of ax plus b. This is the case where you have to be careful. A in this particular case is negative 227.27. That's my y-intercept. My slope is b, 11.11. So I can get this from that linear regression t-test, or I can go to stat, calc, linear regression, ax plus b. Now my values for my x values are list 1, y values are list 2. And then over here what I'm going to do is I'm going to store my linear regression equation under my y equal button. So I'm going to go to vars, y vars, function, and then I want to store it in y1. And then I'll go here to calculate. And now I don't have all that extra information. I just have the information that gives me my y-intercept and my slope. Now you have to be careful here. A is my slope. So in this particular case, since A is in front of the x, A is going to be equal to your slope. So in this case, A is slope, and it's equal to 11.11, we'll say. B is your y-intercept, and it's equal to negative 227.27. Now I rounded these to hundredths to 2 places, but my math lab could ask you to round it to 3 places or thousandths as well. So my regression equation is going to be equal to y hat equals 11.11x minus 227.27. Now you have to be careful how you enter this. In my math lab, they'll have x for you, and you need to make sure you put the value of slope in front of it. Now another way you could write the same thing is equal to negative 227.27 plus 11.11x. These are the same thing, just a different order. But remember, the value in front of your coefficient is told right here to be a, so you need to make sure you have it in the right spot. So that's calculating the line of best fit. Now, a long time ago in this question, they asked us to predict weight, if appropriate. We already decided it was appropriate. So predict weight if chest width is, let's go ahead and scroll up and look. So predict weight if chest width is, here it is finally, 57 inches. So we're going to come down here and we're going to do this predict weight if chest width is 57 inches. So this basically means x is equal to 57. So we can do that. So that's y hat equals 11.11x, x is 57, minus 227.27. So let's go ahead and grab our calculators. So second quit. So I'm going to have 11.11 times 57 minus 227.27. So we can see I get 406 pounds. That seems reasonable. Given the data that we had, that seems very reasonable. So this is equal to 406 pounds. So this is our predicted value. Now let's go ahead and look back at our data. Now remember, down here I had 406 pounds. That definitely seems reasonable. Our smallest value was 282. My largest value was 453. So 408 seems like it falls within this data. The only thing we didn't do here is write a quick summary, and then I'm going to also show you how to do a scatter plot with that line, just as something as an interesting artifact. I don't think you'll ever have to use it, but it kind of gives you a nice little look at the data. So let's go ahead and summarize this real quick. So we predict that a bear with a chest width of 57 inches will weigh about 406 pounds. Let's try that again. About 406 pounds. Okay. Now, the one thing I didn't talk about was a scatter plot with this line of best fit. So let's go ahead and look at that real quick. So we already have all this data in our calculator. Let's go ahead and go to second stat plot. Our stat plots are on. So my variables are L1 and L2. This is my scatter plot. So when I hit graph, it'll graph that. But let's look under y equal. Look what's here. Remember, I automatically asked us to put that line of best fit in y1. That is that line of best fit. So let's go ahead and hit graph. And here is that showing of that line of best fit. Now if I wanted to, from here I could do second calc and value. And this is where I could put in the chest width of that bear, 57 inches. And it'll give me my predicted y value of about 406. Now we got exactly 406 because ours was rounded. This is an exact answer that's not rounded. So I can use my calculator to help me find that as well. So I like looking at that scatter plot with the line. It just kind of gives me a little bit more information and kind of helps me visualize what's going on there. So again, this is the same data. Take up a little space here. So this is that line of best fit. So this is the equation of that y hat and this is plugging in at 57, and here you can see how we get this value back out. Okay, so I like looking at this scatter plot with that line of best fit. It just provides a little extra information and is helpful to me. Okay, let's go ahead and look at another example. This example I'm not going to run through in its entirety, but it might cause a little bit of confusion when you get to it, so I want to make sure you know how to get started with it. So for this example, they ask you to look at a scatter plot of data, and they ask you to find the regression equation for all 10 data points. So again, we're not going to run through this because I think that you'll be fine once you see how the setup will work. So they ask you to use the regression equation on all 10 points. So find y hat equal ax plus b, or a plus bx, however you want to look at it, for all 10 points. So you're going to have to take these points that you see on the graph and translate them into L1 and L2. So basically L1 and L2. Now let's let L1 equal my x values and L2 equal my y values. So for this ordered pair, this would be the ordered pair x equal 1, y equal 8. So this would be 1, 8. Now for this point, this would be the ordered pair 3, 3. This point would be 3, 4. This point would be 3, 5. So 3, 3, 3, 4, and 3, 5. And then you can see that we have the same thing for 4, 3, 4, 4, and 4, 5. And then we'll have the same thing for 5, 3, 5, 4, 5, 5. Okay, so I would find y hat for this data set. So I'd go to your calculator and you'd go to Stat, Edit, and you'd plug in all these values for L1 and L2. Then you'd go to Stat, Calc, and then you'd choose Linear Regression, ax plus b. Make sure you understand which is A. A is your slope here. And if you get these backward, that will kind of mess things up for your answer, so be very careful about this. And then you'd go ahead and enter your linear equation. Then it's going to say find y hat for all of the 9 clustered points and omitting this one. So what you would do then is you would omit this first one and then find your values for y hat for just these remaining 9 values and then compare them. So what you need to do is to take the scatter plot and translate those into ordered pairs. And I think you can do that pretty easily. I just kind of wanted to give you an overview of that, so when you ran into this type of problem, you knew how to get started. Okay, we are going to run through one more problem. And for this problem, we're going to be looking at specifically, let's look at something with blood pressure. Okay, so first of all, let's go ahead and have a look at the data. So it says the data below show systolic and diastolic blood pressure of certain people. So we're trying to see if there's a relationship between the two, systolic and diastolic. It says find the regression equation, letting the first variable be the independent variable. So that means we're going to use this first variable to be my independent variable x, so we're going to put this in L1. And we're going to try and predict diastolic, which will be my y value in L2. Now, this should not be for S person, it should be, say, for A person. Let me erase that a little bit better. So for A person, with a systolic reading of 146. Well, we won't worry about this quite yet. We want to just get through the basic parts of, is this appropriate to use correlation, linear correlation or linear regression. So the first thing that we'll do is we'll look at the data. So we'll go to Stat, Edit. Of course, we'll go ahead and clear both of those. And we'll go ahead and start entering our data. So in L1, I want 120, 119. I'm entering all of the blood pressures that are the systolic blood pressures. 128, 124, 149, 130, 122, 142. Okay, now we want the corresponding y value, so we have to keep our ordering. So 61, 88, 67, 61, 88, 67, 66, 108, 96, 89, and 80. Okay, so first thing I think I'd like to do is to look at a scatter plot. Before I do that, I want to go under y equal and make sure I clear this out for my last problem. Let's go to second stat plot. We want to turn our plots on. Scatter plot. X list is L1 and L2 for my y, and let's hit graph. And again, we may have to go to our zoom stat. So we go to zoom. Now zoom stat is number 9 for me. You can hit number 9, or you can actually arrow down to zoom stat and hit enter. Okay, so here's my correlation. You know, this doesn't look very linear. This top part looks linear, this bottom part looks linear, but taken as a whole, this doesn't look very linear. So I'm not sure if this will pass muster or not to say that rho does not equal 0. So here's my scatter plot. So my concern here is this doesn't appear to be very linear. I don't know if it's going to pass that correlation coefficient test of rho equals 0 versus rho not equal to 0. Okay, so let's go ahead and open up our calculators again. Let's go into stat, tests, because we're trying to find our value for r. And you can scroll up or down, but I'm looking for linear regression t-test. So I want L1, L2, and I don't really care about the not equal to case because that's not really what I'm testing here. I don't want it to go into my regression equation, and I'll just hit calculate, and then I'll scroll down until I see r, because that's really what I'm interested in. So my value of r, it is greater than 0, but it is not really close to 1. It's 0.548, so r equals 0.548. So this is my correlation coefficient. This is the strength of the linear correlation between systolic and diastolic blood pressure. Okay, so to get started, we need to check to see if the two variables are related. So 1. First step, we want to check to see if there is a linear correlation between systolic and diastolic blood pressure. Okay, so the first step here would be to go ahead and state HO and HA. So my HO, again, is always the equal to case. So this is rho equals 0 versus the alternative rho not equals 0. So this is no linear correlation. And this means there is a linear correlation. So my value for alpha was 0.05. My test statistic, that was that value of r that we just calculated with our calculators. This is 0.548. Next, we need to go ahead and have my critical values. Now, in order to find my critical values, I need to know my sample size. So So let's go ahead and look up here for my sample size 1, 2, 3, 4, 5, 6, 7, 8 pairs. And alpha equals 0.05. Okay, so now to find that critical value, we'll go ahead and open up our tables. So this is alpha equal 8. And then we're looking under the 0.05 column. And you can see that these overlap right here. So my critical value is 0.707. So critical value 0.707. Okay, let's go ahead and look at our decision rules. So if the absolute value of R is greater than my critical value, I will reject HO. And that means I do have a linear correlation. That's kind of hard to read. Let's fix that. So that would imply that I have some sort of linear correlation. I don't know if that's easy to read, but it's not as squished. The absolute value of R less than my critical value would mean I'd fail to reject HO. And this would mean I have no linear correlation. Okay, so now let's go ahead and make that decision. So for my decision, I need to know R. In this case was that what was that, 0.548. And I need to know my critical value, which is 0.707. So the absolute value of R would be the absolute value of 0.548. That's going to be less than 0.707. So I need to fail to reject HO. This is new. So there's no linear correlation. Okay, so this is a first. So because there's no linear correlation, when I write my summary, I'm going to have to say linear regression is not appropriate. The data supports the conclusion that the variables and our variables here in this particular case were, to refresh my memory, systolic and diastolic blood pressure. Are not linearly correlated. Now, the big important takeaway from this then is therefore linear regression / prediction is not appropriate. So we need to use Y bar for all prediction. So no matter what X is, I respond with Y bar because that's my best guess. Okay, so let's go ahead and look back up at my steps here. So check to see if there's a linear correlation between systolic and diastolic blood pressure. We decided there wasn't. So our steps change. So step 2, we use Y bar for all prediction. So I don't even have to find a Y hat. Now if you look back at our original, hopefully I'm not giving you vertigo or a headache here by scrolling, but we have a systolic reading of 146 is what I'm given, and then I'm asked to predict my diastolic. So we want to predict diastolic given a systolic of 146. And you know what? The 146 doesn't really even matter because I'm always going to respond with y bar. Now what is y bar? If you remember from our table, here we go again. So y bar was diastolic. Okay, so y bar was diastolic, which was L2. So this is the average diastolic blood pressure. So remember, we used y bar for L1, or sorry, L2, so I'm just basically looking at L2 bar. So let's go ahead and look at our calculator. We'd go to Stat, Calc, one variable statistics. We haven't used this one in a while. But under my list, instead of using L1, I'll want to use L2. So that's under second L2, and then we just go to Calculate. And I'm going to take a screenshot of this first before I hit Calculate as a reminder of the steps here. Let's try that again. So now we'll see the word calculate. Okay. Now let's calculate this value. So there it is, 81.875. That's really the only value on here that ends up mattering. So just this first one. I don't really care about the rest. Now I don't even care about the value that I plugged in for systolic. It's just saying they're not linearly correlated, so X doesn't matter. What matters is just what is the average of the Y's. That's my best guess. So my averages here would be 81, and of course round it to however my math lab says to round it, 0.875. And this is a diastolic blood pressure. And they are measured in mmHgs. Okay, so this would be my best prediction. I don't have to find a y hat. So it's really important that you run through that hypothesis test of rho equals 0 versus rho not equal to 0. Don't skip that, because based on that outcome, you'll either have to calculate y hat or not. So it is very important to do that. As usual, if you have questions, please let me know. Bring them to class, stop by my office, or you're also welcome to go to the Math Center. Good luck on this assignment.